part of this course. So that is, we will apply these ideas that we have learned of dipole, dipole radiation, of relativistic effects on radiation, and we'll apply it to some common astrophysical radiation processes. So today we'll start with something called Bremstrolum. I already gave a little bit of a background on it. It's very common in astrophysics. So let's sort of get started. Oops. Where did it go? Okay, here. So in some sense, this is sort of the second half of the course, and so Bremstrolum. So basically, this is a German word which stands for breaking radiation. Strahlung perhaps means radiation. So this is breaking radiation. So the idea is that the electrons are, this is radiation coming from fully ionized plasma. So you have, protons and you have electrons sort of, distributed thermally. And these electrons are moving faster than the protons because they are lighter, right? If the plasma has the temperature T, then thermal energy of electrons is kT over me, whereas the thermal energy of the protons is kT over mp, and we know that mp is 2000 times faster, so square root of 2000 is about 40, 50. So electrons are about 43 times faster. Okay. The other thing is electrons are light, so they are also undergoing fast acceleration. So we know that Larmor formula is 2/3 E squared A squared by C cubed. So the species which are accelerated more will radiate more. So naturally electrons are much more radiative than protons, because for the same force, acceleration is 2000 times higher for electrons than for protons. So this is like a very fundamental fact, that in most radiative processes we consider only electrons because they are lower mass and their accelerations are high. Okay, so let's get started with the Bremstrolum. Last time I also said that this is also called free emission, because the electrons are free before they interact with the proton, and after the interaction they are also free, unlike bound transition or a free bound transition in which electron becomes bound to the proton. Okay. So this is sort of the schematic picture. We have a proton and we have we have these electrons. So far from the proton, they are traveling in a straight line, but because they get attracted because of electrostatic attraction, so this is sort of like a deflection of electron because of the protons. So a few things before we go on to quantitatively deal with it. Right, so why is this free? Because electron was free before the interaction and is again sort of moving at a constant speed free after the interaction. Okay, so we will be actually, this problem can satisfactorily be solved quantum mechanically, but as usual, we will actually treat it classically, and we will introduce quantum corrections in terms of something called Gauss factors. So this is very common in a lot of classical treatment of radiation. The formulae that come out of the more accurate calculation can actually be incorporated in the form of that we get from classical calculation. That is, we ignore the quantum nature of photons. And we will actually be doing non-relativistic treatment, which means that typical velocity of the electron, which is kT over me, is much less than c. Okay. Okay, so first fact is that right, if you have, say, electrons will also interact with electrons, right? So if you have an electron coming towards an electron, they are repelled, and so this electron experiences a motion toward that direction, but this electron also is repelled. It experiences motion away from this electron. So for like charges, right? If it is a two-body interaction, for like charges, the dipole moment, right, which is equal to summation qi ri, right? And since charges are the same, it's just summation ri, which is equal to a constant. Why is this constant? Because these are internal forces between two electrons, and if you have only internal forces, the center of mass is is not accelerated, right? And we recall, right, when we dealt with the collection of charges, we said that it's d double dot. When that is not equal to 0, that's when we have radiation. But in this case of like particles, like charges and the same masses, right? So, for example, electron-electron collision will not give rise to any radiation because the dipole moment is conserved, right? Because this electron is, is actually experiencing a force in that direction. This is experiencing a force in that direction, acceleration in that direction. So, acceleration of this electron plus the acceleration of this electron. So QIs are the same. So summation of the two accelerations is equal to 0 because these are internal forces, right? So in such interactions, the interaction between like charges need not be considered because there is no net change of dipole moment in such interactions. So so this is one thing to keep in mind. So now we'll treat. So the other thing is we can actually treat. So since MP, the proton mass is say 2,000 times electron mass, we can take protons at rest. Right, the velocities are much smaller. Okay. So let's consider a proton which is at rest and an electron which comes and collides with it. So here we are not, so in a plasma, a collision is not a head-on collision like among molecules, right? If you have two molecules, we consider them that they are colliding when they physically touch each other. That is, they come within the size of the molecule of each other. But in case of a plasma, what happens is the electron and proton need not physically collide, right? Because they are interacting by electric forces, which is a long-range force. So if B is this impact parameter, even for large B, electrons can be sufficiently scattered and feel, their velocity changes. So unlike molecules which only interact through close range van der Waals type forces, in a plasma, electrons and protons have long range interactions. So this is one thing. So we have to consider, large impact parameters. This B is the impact parameter. Okay, so let's treat this problem. Let's consider this to be a general ion. So this has a charge Ze, and this is an electron with charge minus E. E is, I'm taking small e to be the electronic, the charge of a proton, which is positive. So the charge of an electron is minus E. So let me actually, so let me actually show. So let my coordinate system be centered at the location of the proton, of the ion actually, since I'm considering Ze. So let this R be the the coordinate of the electron. So what is the dipole moment? So if you are considering only one electron interacting with one ion, the dipole moment is given by minus E R, right? Summation Qi Ri. And so what is d double dot? Right? D double dot is this acceleration term, which is very, very important for radiation. This is equal to minus E R double dot. Okay, which is nothing but minus E V dot. If V is the electron's velocity, R is the electron's coordinate, this is your double derivative of your dipole. Okay. Right. So you have a charge which is coming from far away. It's only sort of feeling this acceleration for a little while, right? From here to here. Initially, it's traveling in almost a straight line. Finally, it's traveling in almost a straight line. Only in this sort of small duration in which it's nearby the positive charge, it's experiencing acceleration. So mainly during that time, it will be radiating, because at that time, acceleration is non-zero. So this is this. So what about so this isn't real, this V dot is a function of time, right? So this is a function of time. Similarly, D double dot is a function of time. We can actually look at this in Fourier space also, right? If you recall, we always went to the Fourier space because we want the behavior, right? How much power comes at what frequency? So if you recall, we had this, if we just take a Fourier transform of this equation, we get D double dot, D double dot omega. So this D hat is like the Fourier transform of D. Okay, and this is the second derivative, which is nothing but minus omega squared D hat omega. So this is the left hand side, and the right hand side is minus E V dot T. Right, so we have to take the Fourier transform, and that's nothing but e to the I omega t dt integral 1 by 2 pi. So this is your Fourier transform on the right hand side. So this is how your dipole moment as a function of frequency is given by. Okay. Now, as I said, we are considering small angle scattering. We are considering right. So the acceleration only happens. So acceleration non-zero for this short time tau, which is of order b by v, right? So this b is the impact parameter. So so this distance is roughly like 2b, right? Or of order b, and the particle, to the force that acts on this electron because of this because of this ion is acting in the line, in the direction of the line joining the two charges. So if we consider small angle scattering, that is, this angle is small, right? That the collision is not a head-on. We are not considering collisions like this. We are considering sort of small angle collisions. The reason being that these collisions are extremely rare, right? The head-on collisions where the electron, velocity is sufficiently, in fact, sufficiently changed, are rare because the size of the proton is small. So non-zero acceleration occurs for the time of order the crossing time, the impact parameter divided by the velocity of the electron. Or we can also call this collision time. Okay, so we can actually consider two regimes in this frequency, right? This when we integrate this, this will be a function of frequency. What are the two regimes? Omega tau much less than 1 and omega tau much greater than 1. Right, so basically what are these two times? So these are the frequency, this is low frequency regime, this is high frequency regime, and so in the high frequency regime, right, so most of the acceleration, this term is non-zero basically, only for time period of order tau, right? So if we are considering high frequency case, right, if you are considering the high frequency case, this so in this regime, e to the I omega t oscillates a lot, right? So basically you have some v dot over this path, and this term uh, is oscillating a lot because we are considering the high frequency limit. So it contributes sometimes by plus sign, minus sign. So in the high frequency limit, this integral, the Fourier transform, goes to 0, right? Because this is oscillating, this is some sort of small term which is changing slowly with time. I mean, this varies on a time scale tau. So if this term varies on a time scale much shorter than tau, then if you integrate it over time, this adds up to 0. So in this regime, we get d tilde omega is about, is roughly 0. In this regime, when omega tau is much less than 1, we are considering low frequency limit, then this term is almost a constant. The phase factor is almost a constant, so your d tilde omega minus omega squared e tilde omega is equal to minus e by 2 pi, and we can take this phase to be 0 without loss of generality. So this is nothing but v dot dt, right? This integral, and this is nothing but change in velocity, right? V dot dt is nothing but this change in velocity. So the final velocity, initial velocity, and this is the change in velocity delta v. So this is v initial, this is v final, this is equal to v final minus v initial, right? So so this is so basically what we have is d tilde omega. The Fourier transform of the dipole moment is equal to e by 2 pi omega square to v, and 0 for this is for omega tau much less than 1. This is for omega tau much greater than 1. So this is the low frequency limit, and this is the high frequency limit. So basically, you don't see radiation at frequency higher than the frequency corresponding to this crossing time, right? For tau, for frequency omega greater than b by v. Right? This is omega less than b by v. I mean, this is easy to understand, right? Because the time scale for this acceleration is tau. So only for low frequencies will you experience any acceleration, not for high frequency, because all those phases oscillate and give you 0. Excuse me. Okay. Any question? Okay, So the setup is clear, right? That we have a single electron, we are considering a single ion, and we are calculating the Fourier transform of this dipole moment. Now we will actually use the dipole formula that we derived previously, right? If you recall, we derived that this dw by d omega, right? How much energy is radiated between frequencies omega and omega plus d omega. This is given by 8 pi by 3 omega to the 4 c cube d tilde omega whole square, right? This is not, this is sort of a derivative of the Larmor radiation formula. If you have collection of charges, then you can actually think of this dipole moment. So this is how energy radiated varies as a function of frequency. Okay. So basically, if we plug this in here, so this becomes equal to 2/3 e squared by pi c cube, right? So this omega 4 and this d tilde square, the omegas go away, right? So this omega square, the whole square, and this omega to the 4 will cancel, and we have delta v square, and this is 0 for omega tau less than 1. So at low frequency you have radiation, but at high frequency you because of this cancellation of these phases, you get 0. Okay. So this is the energy coming out in some frequency range, omega to omega plus t omega. What about delta V? We need now delta V. How do we calculate this? Let's go back and draw this thing again. So you have an electron. So it's sort of undergoing this scattering. So let's consider this R. Right. So, and this is the impact parameter B. So what is V? So if you're considering small scale, a small angle scattering, basically this is exaggerated. What I'm saying is delta V. So the parallel velocity more or less remains the same, but delta V is really about delta V perp. It's happening in the perpendicular direction. The velocity changes in the perpendicular direction, and that's why this angle is small. Okay, so this is small angle scattering of electrons over protons. So scattering can actually be used, scattering is nothing but collision. Here we are considering particle-particle collision. Previously, when we talked about scattering, we were considering photon-particle interaction. So what is this? So as I said, delta V is almost delta V perp. And what is delta V perp? Change in perpendicular velocity is equal to F perp divided by mass dt, right? So this. So we actually, let me just explain what I write down. So what I'm doing is, so this, when the particle comes here, this is time equal to 0. Okay, and time equals infinity, particle is at minus infinity, time equals plus infinity, particle is at plus infinity. What is F perp? What is the force acting in the direction perpendicular to the direction of the velocity of the electron? Right, so what is it? What is F perp? Right, so the force acting along the line joining these two charges is equal to ZE squared. So this is ZE and this is E. So this is ZE squared by R squared, right? But we have to take this perpendicular component of this. So if this is angle theta, we have to take sine theta, but sine theta is nothing but B by R, right? So this is the magnitude of force acting in the perpendicular direction. And what is R? R is nothing but B squared plus V squared T squared, right? So at time t equal to 0, the charge is right here, right? And at earlier times, you know, this is just Pythagoras theorem that the two perpendiculars are B and VT. So this is your magnitude of the distance. So what is delta V perp? So delta V. So let's forget about the vector sign, because we know that this will be in this direction. So delta V perp equals ZE squared by M. So this M is of course the electron charge, because the electron is doing all the moving. Proton is so massive that we can consider it at rest. And we have this B dt over is this clear? So this is just R cube, right? This is B squared plus V squared T squared 3 by 2, which is R cube, and this is B dt. So basically this is the magnitude of change in the perpendicular direction of velocity. See, the force in the parallel direction is, you know, at this point it's being pulled in this direction, at this point it's being pulled in the opposite direction. So delta V parallel for these small scale scattering is sort of small, but delta V perp adds up in the same direction. So it's a sort of and you know, this is exaggerated. You know, this particle is essentially going like this, very small angle scattering, because these are what dominate. This is small. I mean, here I have made it very large. So you know, you should almost consider it as going in a straight line. You know, just tilting a little bit. Anyway, we can actually calculate this integral. So at t equal to 0, the distance is the minimum, the force is maximum, which happens to be the impact parameter. So if we do that, this integral is quite simple to do. What do we get? We get this is equal to twice Z E squared by M B B. So let's say Z E squared by M, and this so this should be B times T, and this is B cube. So time by B squared. Dimensionally, this is time divided by B squared, which is nothing but this. Okay, so this integral is easy to do. So this is the change in velocity in the perpendicular direction. And what is delta V perp by V? And V is almost the V parallel. So that's like twice Z E squared by M V V squared. And I'm assuming this to be much less than 1. So this calculation assumes this to be much less than 1. So for small scale scattering, for small angle scattering and single collision, what do we get for this guy? So now we can actually plug in for delta V from here. So this formula becomes 8 by 3 pi. So we have to just plug in this guy, right, in this equation. So we have delta V squared. So 4 to the 8 by 3 pi Z square e to the 6, right? Because there are two, you know, there is e square here and e to the 4 from delta V square is 6 by m squared V squared B squared, right, for omega tau much less than 1, and 0 of course for omega tau much greater than 1. This is high frequency limit. Okay. Right, so this B by V tau equals B by V is nothing but the crossing time, right? How fast does it cross the distance of order the impact parameter? Okay, so if on the frequencies longer or on frequencies smaller than the crossing frequency, you get this, and for higher frequency you get 0. Okay. Right. So this is like ZE square by B. ZE square by B is like your potential energy, right? Charge Q1 Q2 by R divided by half mv square. This is kinetic energy. So potential energy divided by kinetic energy is much less than 1. For these small scale, small angle scatterings, this is what is true, right? It's easy to see this, half mv squared. This is kinetic energy. ZE squared by B is potential energy. Okay, so this was for a fixed V. This is an expression. This is an expression for a fixed particle velocity, electron mass, and a fixed impact parameter B. Okay, but now what we want is we allow all the impact parameters, and then we want to calculate what would be the integrated radiation because of all these, sum over all these impact parameters. So how do we do that? Just a sec. So now we consider a medium. So let me actually put a little bit of a. So consider a medium with electron number density Ne, ion number density Ni, and still a fixed velocity, fixed ion and electron velocity V. Okay, so what do we do? So let me write down. So dW by dt, d omega dV. Right. So this is like power per unit volume. Power radiated per unit volume per unit frequency. This is equal to. So this is energy per unit frequency due to a single electron. Okay. Now, if you have electrons and ions interacting, right? If you have many ions, they will scatter more. These electrons. If you have many electrons, they will also get scattered much more. So this power goes like Ne Ni, because it's directly proportional to the number of scatterers and number of electrons. And right, so this is Ne Ni, and we want to calculate, right? So dW by d omega for a given impact parameter B, right? So this is nothing but this. This is dW by d omega for a given impact parameter B. So then we times 2 pi b dB, right, times the velocity of these electrons. So right, so this 2 pi b dP is this this, if you consider the impact parameter B. So this 2 pi b dB is the area of this annulus of size dB, right? So this is the area of this annulus, and we are considering an electron number density Ne moving with velocity V. So this Ne times V times 2 pi b dB is what? This is number per unit volume of electrons. This is area times, so this times this is number of electrons crossing this annulus per unit time. So number density of electrons times the velocity of electrons times the area of this annulus. So this is Ne times V. This is just flux of electrons. Flux times area is the total number of electrons per unit time. Okay, so and this multiplication by Ni gives you this dV per unit volume, because this is number of ions per unit volume, and this factor gives you this division by dt. Is this clear? So this is like a standard calculation where we have some scattering cross section which is sort of embedded in this, and then we sort of sum over all these impact parameters. Okay, now this summation goes over, you know, some B min to B max. Right, so the range of impact parameters. So this is what? This is energy, you know, energy erg per second per hertz per centimeter cube. So this is like your emissivity, like epsilon mu. Okay. Now the question is, what do we put for this B min and B max, the range of impact parameters? Okay. Now, right. So we were assuming small angle scattering. So if your B is smaller and smaller, the angle is larger, right? So so what is this delta theta? The change in velocity. So delta, I mean, this is nothing but delta theta, or sine delta theta to be more precise. But if we assume delta theta to be small, right? So delta theta is, this is V and this is V perp, and tan delta theta, actually tan delta theta is equal to delta V perp by V. So if we are assuming this, so this means that B just a second. Right, so so if we put delta V perp by V is equal to 1 of order 1, we get B has to be bigger than mv square by 2z e squared, right? Just from this, so we are sort of small angle scattering. So this B has to be greater than this. So this is the value of B min. Oops, just a second. Am I doing it right? Z. Right, so B min has to be sorry, this is inverse of that, my bad. Oops. Now that the screen is full, it takes a lot of time to respond. Okay, so right, this will give you B much greater than M Just a second. Right. So we can actually write, let's just, these factors of 4 and pi and so on are just there for consistency with the convention in the literature. But this is actually an order of magnitude. Right. So this is order of magnitude estimate. So B has to be bigger than, not much bigger than B min. Right? Because otherwise this small angle scattering assumption breaks down, and this this expression for delta V perp changes. So B has to be greater than this value. So we can actually put B min to be this, or right. So this is one estimate of B min. What about B max? So this upper cutoff, this integral. So B has to be greater than B min. What about B max? See here, we are assuming omega tau to be much less than 1, right? So what was tau? Tau was B by V. So we are assuming omega B by V much less than 1. So B has to be much less than V by omega, right? So we can actually take B max to be V by omega. Okay, so this is the, this is the cutoff beyond which dw d omega becomes 0. Okay, so this is the value of B max. This is one estimate of B min. Right, there is another estimate of B min, which is inspired from quantum mechanics, and that goes as follows. Right, so if velocity, right, so we know the uncertainty principle delta x, delta p is greater than or equal to h cross, and if we take delta x to be order b, the impact parameter, and delta p to be order the momentum of the electron, which is mv. But this is again an order of magnitude estimate, and the exact calculation can only be done quantum mechanically. So this, if we use this, this gives you another B min, which is quantum mechanical. So B min is equal to h cross by delta p, which is mv. Or in fact, let's forget about h cross. This is h by mv. Sorry, not mp. So again, as I said, these factor of 4, pi, and so on. I'm just being consistent with the book and the literature. So there are two values of B min that we got. One, this is the classical value, right? This is the value. If your B is less than this, your small scale, your small angle scattering formula breaks down. If your B is smaller than this, then this classical treatment breaks down. Basically, the particles are quite close, and you have to worry about uncertainty principle, right? If B is very, very close to this, if the electron is very, very close to the proton or the ion, then you have to worry about quantum mechanical effects. That's when this constraint comes. This is classical. This is when the scattering is no longer a small angle scattering. So the treatment that we are doing right now breaks down. Now, what value of B min should we use? We have these two estimates. So we should use B min should be equal to the maximum of B, so let's call this B min 1 and this B min 2. So this should be maximum of B min 1 and B min 2. So basically what it means is that you should apply this integral only when both this and this, your B is larger than both this and this. So the integral should be cut off at the larger of these two impact parameters. Okay. So this condition can be actually written in terms of half mv squared if it is greater than the energy, right? This is the Rydberg. This is the energy unit in Bohr's atom, right? One Rydberg is me to the 4 by twice h cross square, right? This is n equals to 1 energy level. Energy of that energy level in Bohr model, right? So if your kinetic energy is much bigger than this binding energy, the quantum binding energy, then you can use the classical formula. So for high velocities, let's see, if v is high, B min is tiny. If V is high, B min is tiny. This is also small, but not as small as number 1. So you should use 2. So if V is large, so this implies use B min 2. Because B min 1 is much smaller. So use this. So for fast moving ions, for fast moving electrons, you should use the quantum mechanical cutoff for this integral. But anyway, the point is, what you will see is, when I expand this out, you will see that this integral is not very sensitive to both either B min or B max, and that's a good thing. Okay, let's see. Let me actually expand this guy out. Let's see. So dW by d omega dV dt. So once we have chosen B min and B max, either this, either that. So B max is the same. This is B max. But B min, there are two possibilities. So this is equal to NE NI 2 pi V Okay, now we have to plug in this dW d omega here. So we have this integral B min to B max. This is 8 by 3 pi z square E6 by m square V square B squared times 2 pi is outside, so times B dB. So this integral becomes dB by B, so which is log, which is d log B. So this is equal to 16 e to the 6 by 3c cube. Oh, where am I missing this c cube factor? Just a second. Just yeah, the integrals and so on are a little ugly and tedious, but they are not hard. Okay, so 8z square e to the 6, 3 pi. I'm missing a c cube here. C cube m squared b squared b squared. Right? I missed this c cube. So that's why there is this c cube here. Okay. M square v. Right? So there is v here and v square here. So this makes it b. Ne ni z squared. Okay, now we have that logarithmic factor, so log b max by b min. Right, so this is the expression. So as I said, the integral doesn't depend very sensitively on value of b max and b min. For example, even if b max is off by a factor of 100, log of 100 is a small number. Log of anything is actually not that big. So the good thing is you have a very weak dependence on both b max and b min. So even if you make a little bit of an error, you're not off by too much. Okay, so what people do is actually people write it in terms of a standard expression, which I'll perhaps write it in red. So we have dw by d omega dv dt is equal to 16 pi e to the 6 by 3 root 3 c cube m square v ne ni z squared gff, which is a function of v at omega. Right, so this is what they write this thing in this form. Right, so what are the important things to notice? The important thing to notice is it's proportional to Ne times Ni, the number density of electrons and the number density of ions. It's proportional to Z squared, the charge of ions. It's proportional to 1 by V. This is another very important dependence. So the faster the electrons are, right, the faster the electrons are, the smaller is the power. Right, because the fast electrons are not accelerated as much. Their crossing time is small. What else? And this is an important factor. This is called Gaunt factor, G-A-U-N-T factor. And this incorporates all these, cutoffs and quantum mechanical and the classical limits on these integrals. But the good thing is this is not very sensitively dependent, right? And you see that these cutoffs and so on depend on the velocity, and they depend on the frequency as well. So this is a factor which depends on velocity and frequency, and it takes care of all these mess. And there are tables. There are tables for this, and people can also do quantum. People do quantum mechanical calculations more self-consistently than what I sort of outlined, and they make these tables of this available for people to use. And this GFF, by comparison, you can actually see is equal to square root of 3 by pi log B max by B min. So you'll see there are like the high velocity and low velocity limits of this GFF, corresponding to this Bmin or this Bmin. So at very high velocities, you should use the quantum mechanical formula, this one. Okay. Now this is an expression for electrons with a given velocity v. Okay. We have integrated over all impact parameters, and what we found, this is another thing. What we found is that it really doesn't depend so sensitively on Bmax or Bmin. And that dependence is absorbed in this ground factor. Okay, so what about instead of a single velocity of electron, we have like a Maxwell Boltzmann distribution of electrons? What in that case? So let's go back. Let's go to a new page, because now this is slowing down. And let's see. So basically what I'm asking is thermal Bremstrolum, right? And I'm considering Maxwell-Boltzmann distribution of electrons, in the sense that the number of electrons is proportional to v squared e to the minus v squared mv squared by twice kt dv, right? This is the Maxwell-Boltzmann distribution, the 1D distribution, where we have v squared e to the minus half mv squared by kt dv. So the number of electrons is proportional to this. Previously, we calculated this expression for power due to an electron with a given velocity v. Now we have to integrate over this distribution of electron velocities. Okay. And we are assuming an isotropic distribution of electrons. That's why you have this Maxwell-Boltzmann relation. The other thing that we have to recall is that if you have an electron of energy half mv squared, right? The h nu of the photon which is produced by this h nu has to be less than, right? So if you have an electron which is getting scattered by a charge, right, and it emits a photon, this h nu has to be less than kinetic energy of the photon of the electron, because that's where the energy is coming from, right? So this is where a photon discreteness effect comes. That is, you cannot have photons with very high frequency. You cannot have many photons with very high frequency. Translates to, because your kinetic energy of electrons will become higher than the h nu of a single photon, right? And this is the energy quantum for a photon of a given frequency nu. So the number of photons has to be very, very small at this frequency. That's what its significance is. So this is a quantum effect, right? Because we are using the energy of a photon to be h nu, and this is like you cannot have, if you have a frequency nu of a photon, a single photon will have energy h nu. It cannot have smaller than this. So the source, if the source of energy available is less than that, you cannot create such a photon. Okay, so what about going from, so there were sort of various integrals that we did, right? We calculated the power for a given impact parameter, then we integrated over the range of impact parameters, then we have this expression for power for a given velocity of electrons. Now we have to integrate over all the electron velocities where the electrons are distributed by this Maxwell-Boltzmann distribution. Okay, so what is it given by? So the power dW by dv dt d omega, the same expression, but now we will actually integrate over the electron distribution. So it goes from V min to infinity. So basically, what is V min? V min is equal to h nu, twice h nu by m. Right? If you have particles with velocity less than V min or speed less than V min, they cannot create photons of frequency h nu, because their kinetic energy is less than the photon energy. So this integral must be cut off at the low value of velocities. So this is this, and we have this expression dw by dv dt d omega for a given velocity. Right? So this is a function of velocity and frequency. Now this is integrated over velocity, so this is only a function of omega or nu. This is v squared e to the minus mv squared by twice kt dv, and we have to normalize it. And how do we normalize it? It's 0 to infinity v squared e to the minus mv squared twice kt dv. Right? So this is just integrating the power expression for electrons with a given velocity v, and then summing it over, weighing it with the Maxwell-Boltzmann distribution. And this is just dividing this in the denominator is just the normalization. Okay. So let's see. Let's rewrite this formula from the last page. It was 16 pi e to the 6 by 3 square root 3 c cube m squared v ne ni z squared gff v comma omega. So the key thing to notice is that there is 1 by v. So this integral on the top is basically integral v min to infinity. It's actually proportional to. So instead of v square, you have v e to the minus mv square by twice kt by dv. And this integral is of the form, mv squared, not m squared. This is mv squared. Right, so this integral is of the form s e to the minus s squared ds, which is very easy to do, s min to infinity. And this will just give you, this is e to the minus t dt type of an integral. So this is easy to do. This is also not a hard integral to do. These are the standard s squared e to the minus s squared ds type integrals. When you do e to the minus s squared ds, this type of integral, you also learn to do these. So what do we get? Now the key thing to notice here is this. Here you have v, and at the bottom you have this v squared, right? So let me actually write down the expression here, and then we'll talk about it. This integral is sort of proportional to e to the minus s min squared. So what does this integral become? And also recall that omega equals 2 pi nu. So you can actually express this in terms of frequency nu rather than the angular frequency omega. So what do we have? dw by dv dt d nu is equal to Right, so let's just see what this integral should give you. Right, so this should just give you v cube, and v is nothing but kt by m. So this, I mean, there's v square and there's dv, and there's the exponential thing. So just by dimensional analysis, this is what it should give you. And the top integral should give you v squared, which is kt by m only, right? So when you have kt by m divided by kt by m to 3 by 2, there is a t to the minus 1/2 dependence of this guy. Okay, so let me actually write down. So this is the final expression, 2 to the 5 pi e to the 6. So you will never have to remember all these things because these are available in standard textbooks. What's important to keep in mind is the dependence on important things like temperature, frequency. Right? These fundamental constant dependencies, no one needs to sort of recall. This is important, t to the minus 1/2. Z squared, this is also important. Ne and I, of course, this is also important. E to the minus h nu by kt. GFF bar. And so this is also another gone factor, but this is like a velocity integrated gone factor. So this is also tabulated. Right, and this is actually related to this. This is just right. So this is just the integral of this gone factor when you integrate over all velocities. That's what you get, and it is weighted in a certain way, right? This is weighted with respect to the Maxwell-Boltzmann in a certain way. Okay, so and this GFF it's actually a function of, generally expressed as a function of u, which is nothing but h nu by kt. Right, now recall the velocity has been replaced by temperature because it's been integrated over. Okay, so right, the definition of GFF bar can be written in terms of GFF v comma omega. If you just sort of substitute that back in here, right? If you substitute this definition there, this is what the definition of GFF bar is. But the most important thing about GFF bar is that, so if we plot GFF bar as a function of u, which is equal to h nu by kt, right? It is actually, it does not vary a lot. It sort of has some variation, but suppose this is 10 to the minus 4, so this is a log plot actually on the x-axis. So this is 10 to the minus 4 to 10 over 5 orders of magnitude in frequency. This gone factor changes from 1 to 4. So it actually is a very weak variation, right? So this is weak. That's why it's good to sort of introduce this messy factor, which is not all that important qualitatively in terms of like this a correction factor. This is a quantum mechanical correction factor, not only quantum mechanical, but also this Coulomb logarithmic log B max by B min is there. So even if we don't have to consider the quantum mechanical effect, we have to consider this logarithmic factor. So this is a correction factor. You know, tables are available for this. And this has been like, you know, calibrated and whatnot, both from experiments and from more sophisticated quantum calculations. Okay, so we can actually write, so using this we can actually write epsilon nu ff, right? So this is equal to, just first let me, so this is nothing but dw dv dt d nu. So this is nothing but emissivity, volume emissivity, how much energy is radiated per unit volume, per unit time, per unit frequency, over all solid angles. You're sort of integrated over all solid angles, assuming isotropic distribution of electron velocities. So you know, if you plug in the numbers for all these fundamental parameters, this is what you get: 6.8 times 10 to the minus 38 z squared ne ni t to the minus a half, right? These dependencies are important to know. E to the minus h nu by kt g f bar. So this is also very, very fundamental, right? So this is how emissivity goes as a function of frequency. You see, this is how epsilon nu ff as a function of nu goes. So let's assume it's a long log plot, right? So there is a weak dependence on frequency due to the Gaunt factor. It only changes by a factor of 4. But what it means is that there is, you know, the behavior is sort of like this. So there is this exponential cutoff factor, right? This is photon discreteness effect. If you go to very high frequency, the number of photons become exponentially rare because, you know, the energy is h nu. So in order to sort of conserve energy, the number of photons be extremely rare because of this photon discreteness effect. So, you know, h nu of order kt. There is this characteristic exponential break for free emission, which is similar to the Wien spectrum, but only at the high frequency side. On the low frequency side, there is a weak dependence on frequency, you know, nu to the minus 0.1 or something like that, or, you know, you can even take it as nu to the 0 because it's very weak and it only comes from the Gaunt factor. So this is the characteristic spectrum of free optically thin emission. Do you get it? So this is, you know, this is thermal emission mechanism because electrons have a thermal velocity distribution. Thermal emission need not be black body, right? If it is optically thin, it is not black body. Okay. So how much time is remaining? Oops. Okay, what I'll actually do is I will, so, you know, this, so we'll spend one more class on Bremstrolum and its sort of related aspects, but let me actually show. So, you know, in the next part of our course, I will actually show you examples of real spectra of various of these mechanisms. So this is you can see what I'm showing, right? There is a slideshow which I have made. Can you see what I'm showing? Hello?
Yes, sir.
Okay. So here I have 4 examples illustrating this Bremstrolum radiation. Okay, so most popular sources of thermal Bremstrolum emission are galaxy clusters, and these are actually real spectra from early generation X-ray telescopes, HIAO, low resolution spectrum, and you see this this is in terms of photons per centimeter square per second per energy. So this is, I actually wish to be able to annotate. So I want this and this on the same slide, same. Okay, nice. So so what are galaxy clusters? So galaxy clusters are basically, these are sort of, in the cosmological structure formation, galaxies form in a hierarchical way. Okay, and there are these cosmological filaments which are sort of accreting. So have some of you seen these beautiful simulations movies of dark matter clustering in the universe? Right? They show filaments and halos. So what happens is these are galaxy clusters. So these form at the intersection of cosmological filaments. So basically, material is attracted because of deep gravitational potential of these galaxy clusters, and these particles sort of thermalize. Their velocities are randomized, and so these are some of the most massive. These are most massive bound structures in the universe. These are called galaxy clusters. So there are like thousands of galaxies in a galaxy cluster, and not only that, it's full of X-ray emitting plasma, which is at 10 to the 7 to 10 to the 8 Kelvin. Okay, and this is thermal plasma. 10 to the 7, 10 to the 8 Kelvin. Electrons are non-relativistic, so it's actually perfectly in the regime of Bremstrolum, thermal Bremstrolum that we studied. Now, if you recall, we had, right, so this was the characteristic spectrum, right, of thermal Bremstrolum. What is plotted here on the right is the number. So this is not, this is number of photons per unit frequency per unit time. Per unit energy. So E is equal to h nu. That's like a trivial. When you're looking at high energy photons, generally people use energy instead of frequency. So nu dt. So this is actually flux, right? The plot, the top two plots show number of photons per unit area, per unit time, per unit energy. So this is like a flux. So this is, flux is proportional to epsilon nu divided by 4 pi d square, where d is the distance of this thing. So so the frequency dependence, right? So basically, what happens is when you go from energy to the number of photons, you have to divide. So dw by d nu dt de, you have to divide by 1 by h nu in order to get the number of photons, right? Because h nu times the number of photons is the energy in those photons. So and h nu is nothing but E. So that's why you expect the slope here on the right hand side curves to be, if it is a single temperature plasma, right? So this guy, you expect it to be proportional to nu to the -1, right? Because dw d nu dt de is proportional to nu to the 0 or nu to the -0.1. You see that this is slightly steeper for two reasons. One is this one, but this is not the main reason. The temperature of this cluster plasma is not a constant. So if you plot temperature as a function of R in these clusters, They have low temperature at the center and high at the outside, but the variation is not much, like it's a factor of 3-4 variation. But because of this temperature variation, it's sort of like combining many single temperature plasmas to give this combined spectrum. And you see that there is a characteristic exponential cutoff, right? At high energies, there is an exponential cutoff. I wish I could annotate these figures. How do I annotate this? So you see there is like a power law here, and then as you go to higher energies, there's like an exponential cutoff. Can you see that by eye? So there is like almost like a power law fall. But as you go to higher energies, this is the exponential cutoff. This is just the e to the minus h nu by kT factor. So this gives you a sense of the temperature of this plasma. This is about like 5 to 10 keV, which I said 10 to the 7 to 10 to the 8 Kelvin plasma. This is another cluster. But you see this power law should have been -1, but this is slightly steeper. And the reason it's steeper is because the temperature is not constant. This is another cluster, Perseus cluster. So people like look at these spectra and they try to, get an estimate for the temperature profile of the galaxy cluster. They try to get the estimate of the distance, because the more photons, you'll get more photons if the cluster is closer. Now what is this? This is the same thing, the flux as a function of energy. But these are observations from galaxy cluster. This is a model spectrum calculated from a plasma code. So what you have is like you give it some electron temperature. For example, here they consider a single temperature plasma. So here you will actually see that the low frequency part is actually pretty steep and has a very weak slope. That's consistent with Gaunt factor, because here we are actually constructing these models for a single temperature plasma. Can you see this flat? The green one is almost flat, the red is also almost flat, and so is the black one. But the black one corresponds to a low temperature plasma, so the exponential cutoff happens at a lower energy. And this green, the green one is for 9 keV plasma, so the exponential cutoff happens at a higher energy. So, and not only do you see this continuum emission, the background continuum, right, which sort of is consistent with the Bremstrolum, you also see these broad lines and narrow lines. These lines are because of bound transitions, right? These are standard atomic lines from highly ionized species, for example, iron species. Even at 1 keV, iron is not fully ionized. It has like very highly ionized iron with only 2-3 electrons in that ion, and they can make bound transitions and cause these lines. So these spectra carry a lot of information, and people use these model spectra to understand the observations of these spectra that you get from real astrophysical systems. So you see this is actually fairly easy to understand, right? The black guy, the black line here has a lower temperature. Two things happen at lower temperature. One, the exponential cutoff happens at a lower photon energy. The other is that these lines become very, very prominent. Can someone guess why the lower temperature plasma has more prominent lines compared to the higher temperature plasma? Anyone, please? It's actually very, very simple. So here is a hint. If you fully ionize a plasma, will there be line transitions? Why does line transition happen? Why does line emission happen? Electron goes from one bound level to another bound level. Now can someone come up with a story for why the low temperature plasma shows many, many more lines compared to the higher temperature plasma in green? No.
Because sir, at low, because temperature is low, this means then the electrons maybe not free, means they can be excited to higher levels, but these are not free, so they can because temperature is low, so they can have certain transition to lower level.
Yes. Right. Exactly correct, Sachin. So at low temperatures, more and more ions have electrons in the bound orbits. So they can make transitions and cause these discrete lines. If you go to very high temperature, the abundance of ions with bound electrons becomes smaller and smaller, and the plasma gets almost fully ionized. Only very high energy, these lines at high energies you see, these are because of very highly ionized iron. Only one electron remains in iron sometimes for at these high temperatures of 9 keV. That's why you only see these prominent iron lines. But the lower ions, which are perhaps due to things like oxygen and so on, they are all totally absent because oxygen is fully ionized. There is no oxygen with one electron. It's fully ionized. And if you have a fully ionized ion, there are no atomic transitions. It is only free transitions, which gives rise to this Bremstrolum. Clear? Okay, so now this three graphs we have talked about. What about this one? This is another example of free emission observed, but now in a H2 region. What is an H2 region? If you have a very uh, bright star, that star emits a lot of photons which are at energies which are in UV. These UV photons can ionize neutral hydrogen around this massive star, and these ionized regions are called H2 regions. So this has gas at 10 to the 4 Kelvin, basically plasma at 10 to the 4 Kelvin. Now these are data points actually. So this bump here is due to just black body emission due to dust, but ignore that. This part of the emission is because of free emission due to this ionized gas around massive stars. So these are called H2 regions. So you see it's almost flat, and at high frequencies there is an exponential cutoff, but at those high frequencies another this thermal emission mechanism dominates. But this portion from 2 to 100 gigahertz is free emission. Okay. Any questions on today's lecture? Okay, then I will upload these slides as well. Okay, then I will. Any other questions? No. Okay. So then I'll end the class. I will stop recording and end the class. Okay.